This series of videos is pretty theoretical. We see two important results. One of them is called Rolle's theorem and the other is called the mean value theorem. But aside from these theorems in and of themselves, we're going to see a bit about the structure of mathematics. I know, sounds heavy. First, let's look at Rolle's theorem. Rolle's theorem starts out with hypotheses and gives a conclusion. Let f be a function such that f is continuous on the closed interval from a to b, f is differentiable on the open interval from a to b, and the function value at a equals the function value at b. Then there's the number c in the open interval from a to b such that f prime of c is equal to 0. The 1, 2, and 3 here are called hypotheses. And the final sentence here is the conclusion. And what Rolle's theorem says is that if 1, 2, and 3 are true, then the conclusion, there's a place where the derivative is 0, is guaranteed. We're going to see a proof of this in a bit, but first I want you to see this in action. We have here an exercise. Verify that the function satisfies the three hypotheses of Rolle's theorem on the given interval, then find all numbers c that satisfy the conclusion of Rolle's theorem. I'm going to combine 1 and 2. F is continuous on the closed interval from -2 to 2, and differentiable on the open interval from -2 to 2, because. So I've said that it's true, but I can't just say it's true. I've got to say why it's true. So I have to speak to f being continuous on the closed interval, f being differentiable on the open interval. I can't imply it. I've got to actually state it. And the reason that these are true is because f is a polynomial function. And we know that a polynomial function is continuous and differentiable on its domain. So now I need to say something about its domain, with domain all real numbers. Now I need to show part 3. Well, f of -2 is equal to -8 minus 8 plus 8 plus 2. That looks to be -6. F of 2, we don't just write down, oh, it equals -6 or whatever. We actually compute it. 8 minus 8 minus 8 plus 2. Oh, look at that. It's -6. So now I've shown all three hypotheses have been satisfied. Now I know there's a number c between -2 and 2 such that the derivative of f is 0 at that number c. Now we find it. We know how to do that. Take a derivative, set it equal to 0, solve the equation, go ahead and do it, come back when you're done. All right, bringing in some vocabulary from a previous series of videos, we were looking for critical numbers. And I have x is equal to -2/3 or 2. We might be tempted to say, hey, those are the answers. Well, number 1, we're supposed to answer in terms of c. All right, fine. Number 2, the number c has to be in the open interval from a to b. So we don't get to include -2 or 2. So here we've got that c is equal to -2/3, which is in the interval. There we are. Let's move on. Let f of x equal the tangent of x. Show that f of 0 is equal to f of pi. Let's do that right now. F of 0 for the tangent function is equal to 0. F of pi for the tangent function, remember, is going to be the sine of pi over the cosine of pi. I'm just dragging this out a little bit, is equal to 0. So f of 0 is equal to f of pi. Okay, cool. But now we're supposed to show that there's no number between 0 and pi such that f prime is equal to 0 at that number. Well, let's do this. F prime of x is equal to the secant squared of x. Okay, so now we're going to look at f prime of x equals 0. That would imply that the secant squared of x is equal to 0. Well, guess what? The range of the secant function is from -infinity. I either need to put an argument or spell it out. So secant function is -infinity to to -1, together with 1 to infinity. Therefore, or thus, the secant squared of x is never equal to 0 for all x. So wait a minute. I've got that I have a tangent function, and I have f of 0 is equal to f of pi. Now that's the number 3 of Rolle's theorem's hypotheses. But what we found is there's no number between 0 and pi such that the derivative for our function is equal to 0. So the question is, why does this not contradict Rolle's theorem? So let me restate here. For the tangent function, we have check and then nope. So what's happening here? It's that f is not continuous on AB, right? So here, like, why doesn't it contradict? This does not contradict Rolle's theorem because f is continuous at pi over 2, which is in the interval from 0 to pi. Sometimes people write things like, oh, well, Rolle's theorem fails. Rolle's theorem doesn't get to fail. It's a theorem. Theorems don't fail. It's the case that if the conclusion doesn't apply, then one of these 3 things isn't true. Because here's what we know. If they were all true, the conclusion is guaranteed. That guarantee, by the way, comes in the form of a proof. And we're going to look at that in the next video.